Hello, my name is Christopher Robert Stum. Apologies for the poor quality in video. Unfortunately, I don't necessarily have the best viable options available at the time, and well, my living spaces are also rather unfit, and as you can see from the heat, it's also quite humid today, but I'll make do with what I have. I do intend to improve the quality of my utensils within the foreseeable future, but for now, this is the hand I'm dealt. So I hope that the quality of the films does not degrade in any way the information that I'm presenting in each of them. So in this film, I'm going to have some fun. I'm going to be discussing the idea that the number 1 is actually equal to 0.9999 repeated. That is the decimal approximation. Now I'm going to discuss this because more often than not, many students are resistant to this initially. They're like, how could this be? You know, surely, perhaps it's very close, even right beside, but it can't be equal to 1. Well, in fact, it is. And I'm going to do 2 ways to demonstrate this. The first, which isn't necessarily a proof, but more so an intuitive demonstration for those who are perhaps more mathematically less literate, as it were. So, suppose that instead of saying it's equal to 1, I define some variable x. Well, we have then that 100x is equal to, in accordance to the definition of multiplication of a decimal by 100, 99.9 repeated. It follows then that 100x minus x is equal to 99.9 repeated minus 0.9 repeated. In accordance to the definition of subtraction, we see that we drop off these infinite decimal repetitions such that the end result produces 99x equal to 99. And so now we see that x is equal to the quotient of 99 divided by 99, and so x is equal to 1. Now again, we haven't proven it, but this is very strong basis for conjecture. So we can make conjecture that by the property of the transitive property of equality, that because x is equal to 1 and in turn is equal to 0.999, that 1 is thus equal to 0.9 repeated. Now the second portion is going to be an actual proof. And the reason that this is not a proof is because it kind of goes like this. The logic is, if I have weights in my hand and I were to place 3 pounds in each hand, but I already had weight to begin with, which I didn't know the weight of, then I couldn't assume that the resulting value after adding the weights would be the same. And the same follows here. Because I don't necessarily know equality to be true, any operation I perform to both sides of the equation can't necessarily said to be true that is equivalent either. Because in order to do that to both sides of the equation, we must know equality to be true. Now the fact that this works is because it is indeed equal, but we have yet to have proven that. And so now I'm going to provide a much more thorough way in which we can, beyond a shadow of a doubt, prove this to be true. This portion will be for the more mathematically literate, but don't be discouraged if this looks like Greek to you, because I intend to post many very informative videos on several topics. So if at this juncture these seem very difficult and burdensome concepts, fret not, because in the future you can come back and see the second half and then glean the same insight that, you know, those who were able to before you could at this point. So don't feel discouraged. You know, I don't want that to feel derogatory or anything. So, you know, just keep in mind that if this looks like Greek, that's okay, because it is. I mean, we'll be using Greek symbols. So, all right. So now we're going to prove, and we're going to be proving by working only one side of the equation. So we're going to leave this as is. We're going to operate only this side and arrive at the fact that it is equal to 1, thus proving equality. And so let's do that. So we see that this is 1 equal to 0.0999 repeated. That's my claim. Well, I can just change this side to 0.999. That doesn't change anything. Well, I want to draw your attention to the fact that this is actually the same as 0.9 plus 0.09 plus 0.009 plus, and we just keep adding 9s. And this is the same number, so we add to infinity. And the proof of that being if you align them up at their decimal and added them vertically, you get 9, 9, 9. and you keep adding those 9. So this is the same number. We've not changed anything. All right, well notice that I could alternatively express this as 9/10, such that this is 1 equal to 9/10 plus 9/100 plus 9/1000. And we keep adding smaller and smaller partials. Notice that we have a constant of 9 for each term. Let's factor that out. So 1 is equal to 9 times 1/10 plus 100th plus 1000 plus, and again we keep adding to infinity. Well, notice also that there's a common power of 10 between these denominators. So we might also write this as 9 times 1/10 to the 1 plus 1 over 10 to the second power plus 1 over 10 to the third power. Let me make that 3 more pronounced. And we keep doing this infinitely. Those of you who are very familiar with math should be rather excited right now, or perhaps if you are familiar and passionate, I suppose. Because this, well, this is an infinite series. We start at some value, and so by the utility of summation notation, we continue to infinity. We observe that we can write 1 equal to 9 times. We have the summation as k goes from, I'm going to call it 1 for now, because we start at 1 to infinity of 1 over 10 to the k power. Interesting. So this is not in standard form, but note that this is a geometric series. Before we can write it and evaluate it, we need to put it in standard form. So let's do that. We're going to change the index that's a starting place to 0. So in doing that, we see that 1 is now equal to 9 times the summation. We're going to mitigate that is reduce it by 1, so we have k equal to 0 to infinity. Since we've reduced that by 1, we must add 1 in turn to that, so that's of 1 over 10 to the k plus 1 power. I'm running out of board space, so I'm going to continue over here. So now we have that 1 is equal to 9 times the summation k equals 0 to infinity. So I want to draw your attention to the fact that 10 to the k plus 1 is really 10 to the k times 10. That is 10 to the k times 10 to the first, in accordance to the properties of exponentiation. So we might write that as 1 over 10 to the k times 1 over 10 to the first, or just 1/10. So let's just simplify that to 1/10. Okay. Now, notice also that we can therefore write this as 9 times the summation as k equals 0 to infinity of any power that's defined to be a finite number. That is, any power such that it's not infinity. 1 raised to that power is going to be 1, right? It's within the, the set of real numbers and such. We have to put some constraints on it. Given that, I can interpret this as 1 to the k power, and it still doesn't change anything. It's still 1 over 10 to the k. But what it affords, that is the advantage it affords me, is that now I can put this as 1 over 10 to the k power times 1 over 10. So now we have a constant 1/10. We can factor that out with to the 9 basically. So now we have that 1 is equal to 9/10 times the summation as k equals 0 to infinity of 1/10 to the k. Since the index starts at 0 and it's to the k power, that is r is to the k power, this is a geometric series. And we see that since r is less than 1, that is 1/10 is less than 1, that it's a convergent geometric series, and so we can evaluate it as 1 equal to 9/10 times a, which here is just 1 over 1 minus r, which is 1/10. And so we have 1 equal to 9/10 times 1 over 10/10 minus 1/10 is just 9/10. here's where it's kind of cool. Since we're taking the inverse of 9/10, it's the reciprocal, which means that 1 is equal to 9/10 times 10/9. We just invert and multiply the fractions. Notice that there's a cancellation of terms such that we really have 1 equal to 1. And so we have proven the statement that we sought to prove. That indeed 1 is equal to 0.999 repeated. That is absolute proof.